welcome back to calculus. So, last time we finished up our review of kind of pre-calculus topics, and now we're going to move to where the meat of the course is really going to get going. We asked two questions in kind of that welcome video and we said these two questions are going to guide all of calculus. One of those questions was, hey, is there a way to generalize the slope of a curve? And we said that might have something to do with these tangent lines. So I asked the question, can we find the equation of a tangent line to the curve at any point? So maybe tangent line there, or perhaps the tangent line to the curve right here. What's an equation for that line, etc., etc. Now, finding equations for those things is going to require some machinery that we don't have yet, called the derivative. But to build up to derivatives, what we're going to do is we're going to look at limits first, and those are going to be a crucial factor in how we define derivatives in a few videos from now. So, what is a limit? Intuitively, you can think of a limit as being what happens when a function gets really, really close to some value, and we're looking at what is happening to the function. So let's do an example, because that's kind of a weird thing to conceptualize, and the definition is going to be a little technical. An example will make it very clear. Let's let f of x equal x squared minus 9 over x plus 3. Now, this function is undefined at x equals negative 3, right? Because x equals negative 3 will give us a 0 in the denominator, and that's bad. Okay, so we have a function undefined there, but let's see what happens as x gets really, really close to negative 3 without actually being negative 3. So I'm going to make two tables. I'm going to make the table for as x gets really, really close to negative 3 from the left, so from below negative 3. And I'm going to make one for as it approaches from the right, so above negative 3. I guess let's do the one from the right first. Yeah, why not? 3 decimal places for good measure. Okay. So all of these numbers are bigger than negative 3, and they're getting really, really close to negative 3 as we go. If we start plugging them into our function, for instance, f of negative 2 would be negative 5, f of negative 2.9 would be negative 5.9, 5.99, 5.999. I calculated all those out ahead of time, but obviously you're just plugging in values for x into the function. Now let's talk about approaching from the left. Maybe with negative 4, negative 3.1, negative 3.01, negative 3.001. Start plugging those values in, we get negative 7, negative 6.1, negative 6.01, negative 6.001. So it seems as x gets really, really close to negative 3, f of x is getting really, really close to negative 6. Even though it's not actually defined at negative 3, right? We can't plug negative 3 into this function. But it looks like f of x is getting really, really close to that. So we're going to develop a limit in order to make that notion kind of formal. For this example specifically, we see that as x goes to negative 3, from both the left and the right, that is important. then f of x is going to go towards 6. So we say that the limit of f of x as x approaches 3 is negative 3, is 6. And we write that as lim x to 3. So limit as x goes to 3 of f of x, right? Or in this case, f of x, I keep saying 3 when I mean negative 3. Goodness graciousness. Negative 3 of f of x, which is the limit as x goes to negative 3, got it that time, of x squared minus 9 over x plus 3, and that's going to be 6, positive. Because as x got really, really close to negative 3 from both the left and the right, f of x got closer and closer to negative 6. Goodness graciousness. Should have been negative 6 all along. Sorry. You'll find with calculus that the most common way to get a problem wrong is to accidentally drop a minus sign. Happens. I'll try to be a bit more careful. Alright, let's do another example. Let's let g of x equal 1 at x equals 0 and x squared for x not equal to 0. Do a quick graph of that function. It's going to look roughly like x squared, except at x equals 0, where we have 1, like that. Okay, so that's our function, and we ask ourselves, what is the limit as x goes to 0 of g of x? Go. Alright, so we look at what happens as x goes towards 0, but as long as x is not equal to 0. Limits are all about what the function, quote unquote, should be doing as it approaches. So if we look at this function g of x here, we see that even though it's defined as 1 at 0, it's really approaching 0, right? That's what the function wants to be doing. It's just because we made a separate definition that it does this kind of weird thing where it has this point of discontinuity. So let's do, I'm going to hypothesize that the limit as x goes to 0 of g of x should be 0, right? Let's see that with our table as well. Again, we need to approach from both the left and the right. These should be g of x's. Alright, well, 0.1, 0.01, 0.001, so that's approaching from the right. Negative 0.1, negative 0.01, negative 0.001, that's approaching from the left. Start plugging those in, you get the following. 0, 1, 1, 2, 3, 4, 5, 1. And then here, you'd also get positive 0.01, 0.0001, and 0.2, 3, 4, 5 zeros, 1. Again, those are just from plugging in to our definition of the function. None of these are equal to 0, so they all fall into that x squared category. And this shows that the limit as x goes to 0 of g of x is 0. Right? Even though the function is defined as 1 right there, we don't care about where the function is actually defined. We care about the limiting process on both sides. So that's nifty. I think we're ready for the formal definition of a limit. So, the formal definition of a limit is a bit technical. Don't worry, we'll kind of go through it and say it a little more casually after we say the kind of hard version. The function f has limit, or the limit, L as x approaches a, where a is just some number. And we write this as lim x to a of f of x is equal to capital L if for every epsilon greater than 0, epsilon is just some positive number. We think of epsilon getting really, really small. If for every epsilon greater than 0, there exists another small number, delta, greater than 0, such that if 0 is less than the absolute value of x minus a less than delta, so if x is not a, but it's closer to a than delta, right? So it's distance less than delta away from a, then the absolute value of f of x minus L, the limit, is less than epsilon. Okay, this definition, clunky, cumbersome, technical. Trying to compute limits with epsilon delta is a useful skill to have in higher mathematics, but this is a beginning calculus course. We're not going to work with the epsilon delta definition ever, but it'd be a crime for me to not write it down. Let's put that into more normal person terms. Informally, the limit as x approaches a of f of x is equal to L. So we have the same situation. If we can make f of x get really close to L as x gets really close to a. And that's all this is saying is, hey, if x is getting really, really close to a, then f of x better be getting really, really close to L. This is what you should think of when you think of a limit. Is, hey, as long as x, let's say our a is here, as long as x is getting closer and closer to a, then f of x is getting really, really close to our limit L. Okay, so that's the informal definition of a limit. Let's do an example. One quick and easy way to calculate a limit is to use a graph if you have one of those available. We kind of saw an example of that previously. Let's do one more. Let's let f of t, maybe, equal t to the fourth minus 1. Let's find, this time it'll be the limit as t approaches 2 of f of t. Alright, using our graph, or our graphing skills, which you should have learned in pre-calculus, how to graph any sort of polynomial that you want, we'll see that the graph of f of t is going to look roughly like this. Here's 1, here's -1, that's also -1, maybe 2 is here, and all the way up here should be 15. So the point 2, 15 is on the graph. We see that as we approach 2 for our x value, from both the left and from the right, f of x gets really, really close to 15 from the left and really, really close to 15 from the right. Therefore, the limit as t goes to 2 of f of t is 15. I think I said x should have been t for that whole example, right? As t goes really, really close to 2 from the left or from the right, f of t gets really, really close to 15. Therefore, limit as t goes to 2 of f of t is 15. Variable name doesn't matter. So, yeah. All right. You might ask yourselves the question, do limits always exist? Unfortunately, the answer to that question is no, they don't. Let's see a situation where a limit doesn't exist. In fact, two situations where limits don't exist. And again, we'll see it graphically. Let f of x equal, you know what, I will preface it. You should probably write this in your notes. Limits don't always exist. In our example of that, let's let f of x equal 0 when x is less than 1 and 1 for x greater than or equal to 1. And g of x equal 1 over x. Okay, both of these are pretty nice functions to be dealing with. F of x is just going to look like, maybe I'll put f in blue. Okay, this would be our f of x. So it's just, nope, that's not f of x. I shifted it over. This is a 1, not 0. How silly of me. Goes a little further. There we go. I was like, I knew I did a different thing than that. All right. 1, 1. This is our graph of f of x. So a nice, simple function. It's just 0, 0, 0, 0, and then jump up to 1. The only thing to figure out is where the dot should go, closed dot should go, if anywhere. And we see that there's a greater than or equal to sign here, which means we fill it in there. So that's our f of x. How about g of x? Well, 1 over x just looks roughly like this. And that one I am sure about. Okay, there's points on both of these graphs where the limit of the function doesn't exist. Think about where for just a second, and then we'll go through it. All right, so the limit as x goes to 1 of f of x and the limit as x goes to 0 of g of x do not exist. You might ask yourself, well, why don't those limits exist? Let's think about what's happening with fx, and let's think about our definition of the limit. The definition of the limit says as x gets really, really close to a certain value, f of x should be getting really, really close to other value. Well, as x gets really, really close to 1 on the left, f of x is getting really, really close to 0. In fact, it is 0 the whole way. Okay, that's all well and good so far. But then, as we jump over to the right, as x gets really, really close to 1 from the right side, f of x is at 1, not 0. So, there's this unreconcilable jump in the function, right? Different from our example where we had one point of discontinuity that looked like this, because both of those sides were still approaching the same thing. So the limit existed there, but the limit will not exist as x goes to 1 here, because there's a jump where the function is doing different things from different sides. The limit would exist anywhere else on the function, just not right there. G of x has the exact same problem. As x goes towards 0, g of x is both going towards positive infinity and negative infinity. Huge jump. Can't be reconciled. In fact, even if we altered this slightly and maybe said this was the limit, maybe g of x was 1 over x squared instead of 1 over x, we would still say that the limit does not exist. Why? You might say, can't you just say the limit is infinity? Yes, you can. But infinity is not a real number. Infinity is a concept. So the limit still would not exist, even in the case where they're both shooting up towards infinity, or if they were both shooting down towards negative infinity, limit still doesn't exist. We'll be able to say that later, and I'll understand what you mean. And in terms of real numbers, infinity is not a number. All right, so those are two examples of where a limit doesn't exist. And we've so far really only computed limits with graphs and tables. That's all well and good, but if you don't have access to a graph, or if the function is too nasty to graph, that's a problem. And some functions also have really nasty formulas, right? Or some functions don't have formulas at all. So actually plugging in their values in a table would be impossible. Thankfully, some bright spark was like, I have a better way to compute limits. Let's do it. And he took the epsilon delta definition of a limit, and he proved a bunch of things. These are known as the limit laws. And they're going to allow us to use a few limits that are easy to calculate a bunch more limits that would be more difficult to do rigorously. So, suppose that f of x I'll reword that. Let's suppose that the limit as x approaches a of f of x is L, and the limit as x approaches the same a of g of x is m. Okay, so we have two functions, f and g, and as x gets really, really close to a, the limit for both exists. F of x is limiting to L, g of x is limiting to m. What can we say about different combinations of those two limits? Then, 1, the limit as x goes to a of f of x to the rth power is equal to the limit as x goes to a of f of x all to the rth power, aka L to the r. So that's nice. Exponents pull out of limits is what you want to think. Exponents pull out of limits. Rule number 2, the limit as, and this is for any r greater than 0. When r is less than, greater than or equal to 0. When r is less than or 0, it works too, just there's a funky thing where if f of x happens to not be defined, or sorry, if f of x happens to be 0 at a, then it wouldn't exist and things go wrong. But, yeah. So let's just say the law for r greater than or equal to 0, where it will always work. Exponents pull out of limits. Next rule. Limit as x goes to a of a constant c times f of x is equal to c times the limit as x goes to a of f of x, aka c times L. And the way we want to think of this is constants pull out of limits. Scalar multiples. Play nice. Right, all these limit laws are kind of ways of saying different operations that we would do with functions play nice with limits. The definition of a limit is rigged to make that happen. It also jives kind of well with what you would think would happen, which is a nice bonus. 3, the limit as x goes to a of f of x plus g of x is the same as the limit as x goes to a of f of x plus the limit as x goes to a of g of x, aka L plus M. Same thing is true with subtraction. So, limits play nice with addition and subtraction. They also play well with multiplication and division. Limit as x goes to a of f of x times g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x, aka L times m. So that works nicely, and division also works nicely. Limit as x goes to a of f of x divided by g of x is the limit as x goes to a of f of x over the limit as x goes to a of g of x, which is L divided by m. And this also has a slight restriction. This is when m is not equal to 0. So you can't pull the limit out if it would cause you to make a divide by zero error, which I think is a pretty sensible restriction. But other than that, you can. So that's great. Limits work nicely with all the operations we've talked about for functions. Composition, we haven't discussed. Limits don't really do well with that, so don't worry about it for now. But yeah, exponentiation pulls out of limits. Scalar multiples pull out of limits. Sum and difference pull out of limits. Multiplication, division, pull out of limits with the sensible restriction that you can't pull out division if it would make you do a divide by zero error. That's all great. And now we can compute a lot of really complicated limits with a lot less effort. We'll do a few different examples. Let's find the limit as x goes to 4 of x to the 4th plus 1. I will state first as an obvious fact in fact, two obvious facts, plural. The limit as x goes to anything, so just some arbitrary a of the function x is a, right? That's a pretty obvious fact. Straight line, you plug it in. And also, the limit as x approaches a of some constant c is c. Let's think about why that is. Well, a constant function looks something like this, right? It's just a horizontal line. So of course the limit would just be the actual value that we're sticking with. Okay, that's enough for us to compute this limit here. The limit as x goes to 4 of x to the 4th plus 1 is, okay, according to limit law number 3 here, we can split up over the sum. Limit as x goes to 4 of x to the 4th plus limit as x goes to 4 of 1. Okay? Using our first limit law, says that we can pull out an exponent. So this is the limit as x goes to 4 of x to the 4th plus, okay, limit of a constant is the constant, so this is plus 1. And we know that the limit as x goes to 4 of x will just be 4. So this is 4 to the 4th power plus 1, which, let me see here, try to do my multiplication quickly. And we get 4, 16, 64, 256 plus 1, which is 257. Boom. Pretty nice. And we didn't have to mess around with any tables or graphs. Let's do another couple of examples. Let's find the limit as x goes to -1 of the cube root of x minus 1. All right? Well, that is equal to the limit as x goes to, I'll put the extra step in. That's equal to the limit as x goes to -1 of x minus 1 to the 1/3 power. Using standard rules for exponents, right? Cube root is to the 1/3. Using our exponent rule for limits, we can pull that to the outside of the limit. Limit as x goes to -1 of x minus 1, all to the 1/3. Okay, so then that's the limit as x goes to -1 of x minus the limit as x goes to -1 of 1, all to the 1/3. This is -1 minus 1 to the 1/3, which is the cube root of -2. Negative cube root of 2. Same thing. But yeah, let's go with the cube root of -2. Remember, we can take cube roots of negative numbers, just not square roots. Even powers, bad. Odd powers, good. With roots. Okay, so that's not too bad. The more you get experience with this, the more you can see, hey, maybe I can just plug in right here and I'm content doing that rather than splitting it up. But for your first few times, it's helpful to go through all of the possible steps. Also, remember your exponent rules. It does not distribute over subtraction or addition, just over multiplication. Let's do another example. Second eraser. Let's find the limit as x goes to 1 of x plus 1 over x minus 2. Okay? Well, that's equal to the limit as x goes to 1 of x plus 1 over the limit as x goes to 1 of x minus 2. Technically, we only know we can do this if this bottom limit is non-zero. But let's try it, and if this one's 0, then we'll just go and erase it from the start. It won't be 0, though. Okay, so this is the limit as x goes to 1 of x plus the limit as x goes to 1 of 1 divided by the limit as x goes to 1 of x minus the limit as x goes to 1 of 2, which is 1 plus 1 over 1 minus 2, 2 over -1, -2. Bada bing, bada boom. Nice and simple. Alright, so limits play nicely. But what about a limit that doesn't quite play so nice? Alright, let's go to our first limit, the original one that we did, and try to compute it using our limit laws. The limit as x goes to -3 of x squared minus 9 over x plus 3, and hopefully I can avoid dropping negative signs here. Okay? Well, this is maybe the limit as x goes to -3 of x squared minus 9 over the limit as x goes to -3 of x plus 3, limit as x goes to -3 of x squared minus limit as x goes to -3 of 9 over limit as x goes to -3 of x plus limit as x goes to -3 of 3. Okay, x squared, skipping that one step, will go to 9. 9 goes to 9. X will go to -3. 3 will go to 3. And we're left with 0 divided by 0. Well, the fact that we got a 0 on the denominator here, that's real bad, because it means that this wasn't a valid step to do in the first place. And then having another 0 on the top just makes it more confusing, right? We know that this limit exists because we found it, right, using a table. We showed that the limit is equal to -6. So why didn't we get -6 here? I'll tell you why. Okay. This 0 over 0 it's even worse than being undefined. We call 0 over 0 an indeterminate form. Which means it could be actually any number at all, and we don't have a way of choosing which. It could even be infinity, and we don't know. Later on, we will learn a very advanced technique that can just deal with indeterminate forms like that. For now, we're going to have to figure out some way to work with it and make it get to -6. Okay, how can we do that? Well, for now, what we can try to do is rearrange what we have in the limit in such a way that our limit laws play nicely. We know we can't do this. Bad, because this limit would go to 0. So we can't do this first step. What can we do? Well, x squared minus 9 is a polynomial. All polynomials can be factored, so that might be a good place to start. This is the limit as x goes to -3 of x plus 3 times x minus 3 over x plus 3. Now, that's all well and good, right? Now we have a factor of x plus 3 on the top that can cancel with our factor of x plus 3 on the bottom. So, even though these are not the same function, right? This one is undefined at -3. This one is defined at -3. They're the same in the limit, because the limit doesn't care about what happens at -3. It only cares about what happens close to -3. And this is a valid cancellation for all x not equal to -3. But we don't care about x equals -3 when we're working in the limit, as I said before. And now we can evaluate this using our standard limit laws. This is the limit as x goes to -3 of x minus the limit as x goes to -3 of 3. And that glare is real bad, isn't it? I'm kind of blocking it, hopefully. This is equal to -3 minus 3, which is -6. I'm going to stand here long enough to block the glare, let y'all pause and see it, and then I'm going to move back in. Alright. Goodness gracious. Yeah, so the limit became -6 exactly as we wanted it to be. So that's a good way to deal with indeterminate forms. If you have something you can factor, do it, and you can make good cancellations because we're working in the limit. Okay, let's see another example. Let's try to find the limit as h goes to 0, or you know what? H goes to 1. Let's be fancy. Of the square root of h minus 1 divided by h minus 1. Okay, we know that the denominator will give us 0 if we plug in h equals 1, so we're not even going to try to do it the other way because we know it'll go wrong. Top would also give us 0. So we'd have a 0 over 0 situation. Let's figure out how to deal with it. In cases where you can't factor, right? This is polynomial, but it's already factored. This isn't polynomial, can't be factored. In cases where you can't factor things, we choose a clever 1 to multiply by. That's actually a pretty common trick in math, is choosing a clever 1. And what we'll do is we'll choose the same clever 1 that we would try to use if we were rationalizing a denominator, right? Multiplying by the conjugate radical on the top and bottom. Hopefully that name sounds familiar. It's multiplied by the square root of h plus 1 on top and bottom. You could also do negative square root of h minus 1. I choose to do this because it'll turn out a little neater. If we choose this, all we did was flip this minus to a plus on the square root term, and we multiplied the top and bottom by it. Fancy choice of 1. That's valid. And now, if we start simplifying the fraction, this is the limit as h goes to 1 of square root of h squared minus the square root of h plus the square root of h minus 1 divided by h minus 1 times square root of h plus 1. This is just standard foiling. Limit as h goes to 1, square root squared, that's the original thing. So we have h, those two cancel out, we're left with h minus 1 over h minus 1 times square root of h plus 1. And voila, now we have an h minus 1 on the top. They can cancel with an h minus 1 on the bottom. We're left with the limit as h goes to 1 of 1 divided by the square root of h plus 1. And that's all going to work out right nicely as 1 over the square root of 1 plus 1, aka 1 over 2. And there we go. So this is another way to deal with indeterminate forms. Those are the two most major indeterminate forms that are going to come up, at least for now. Polynomials, deal with by factoring. Things where you have a square root, multiply by a proper choice of 1. Typically that's just flipping up one of the pluses to a minus or vice versa, and then multiplying. And then it'll all sort out nicely. Alright, so those are some indeterminate forms. Excuse me. Alright, there are a couple more things that we can cover about limits real quick. Let's talk about limits as x goes to positive or negative infinity. I said that a limit of a function doesn't exist if the function does something like that and shoots up towards infinity. But what if it's not the function shooting up? What if x is just getting really big? That we can actually deal with. In fact, you might have heard of that under the name horizontal asymptote before. We say that the limit as x goes to infinity of f of x is equal to L if f of x gets really close to L that's a little bit crammed together as x grows without bound. Crammed together, but hopefully in a slightly more legible way. Okay, that's a reasonable thing to say. As x gets really, really big, if f of x sort of stabilizes down to L, then the limit as x goes to infinity of f of x is L. Similar for the limit as x goes to negative infinity of f of x. Right, same idea, you say, as x gets really, really negative, what's happening to f of x? Let's look at that one function earlier that had an undefined limit, the step one. So for this example, let's let f of x equal piecewise function 0 for x less than 1 and 1 for x greater than or equal to 1. I think I drew in blue last time. Goes all the way to 1. Open circle there. There. Alright, so even though the limit at 1 doesn't exist, the limit everywhere else does, and in fact, the limit as x goes to infinity of f of x is positive 1. Since we're always on the positive 1 branch, the further and further we go up. And the limit as x goes to negative infinity of f of x is 0. Since we're from here on in the 0 range. So that's nice. We can use this definition to come up with a really powerful theorem. It might not seem powerful at first, but it's important. I do promise that. Theorem. For all n greater than 0, so for all positive exponents, the limit as x goes to infinity or negative infinity of 1 divided by x to the n is going to be equal to 0. Which makes sense, right? As x gets really, really big, the denominator is getting really, really big since we have a positive exponent. 1 divided by something really, really big gets really, really small. So this limit will be 0. And this actually unlocks for us a new technique for dealing with more complicated limits. I'll avoid that side of the board since the glare is coming through blinds. And we'll jump over to here. Okay. Let's try evaluating the limit as x goes to infinity of x cubed minus 1 over x to the 4th plus 2. Okay, well, we can't do it just by plugging in infinity for x, right? Infinity cubed is infinity minus 1. That's infinity. Infinity to the 4th, infinity plus 2 is still infinity. Infinity to over infinity, this is actually another indeterminate form. And you might be like, isn't that just 1? No, and we'll actually see why with this example. Infinity over infinity, here's all I have to say about that. Some infinities are bigger than others, and also growth rate matters. if this is going towards infinity slower than this, something different is going to happen than just 1. And we'll actually see that here. Alright, so let's observe. This limit is equal to the limit, so this is x, limit as x goes to infinity of, I'm going to choose to multiply by 1 divided by the largest power of x on the top and the bottom. Again, another clever choice of 1. 1 over x to the 4th divided by 1 over x to the 4th times x cubed minus 1 times x to the 4th plus 2. Now, we can do this, and let's see why this is useful. Because this gives us the limit as x goes to infinity of 1 over x minus 1 over x to the 4th over 1 plus 2 over x to the 4th. Alright? Go through all of the limit laws. That's actually good practice to do on your own. Is try to apply the limit laws. See what you get. When we meet as a class, then ask me a question if you didn't get that. Yeah, apply the limit laws, and you should end up with, this top part's going to go to 0, this part's going to go to 0, this part's going to go to 1, this part's going to go to 0. So we get 0 divided by 1, which is just 0. So this limit actually goes to 0. How about that? Infinity over infinity, not always 1. Let's do another couple examples. Limit as x goes to infinity. Let's even do negative infinity. Spice that up. Of x to the 5th over x to the 5th plus 1. Again, trying to plug in naively would supposedly give you negative infinity over negative infinity. That is also bad, right? It's really just infinity over infinity. But same bad things happening, indeterminate form. So we can't do it naively, but we can do it via this same method. This is the limit as x goes to negative infinity of 1 over x to the 5th times x to the 5th over 1 over x to the 5th times x to the 5th plus 1. That's the limit as x goes to negative infinity of 1 over 1 plus 1 over x to the 5th. Applying the limit laws multiple times, we get limit as x goes to negative infinity of 1 over the limit as x goes to negative infinity of 1 plus the limit as x goes to negative infinity of 1 over x to the 5th power. Make that a little bigger. Alright, computing all those limits, 1, 1, 0. And we're left with just 1. So, very useful technique. Let's see it one more time. Limit, gotta put my example prefix for all you color coders. The limit as x goes to infinity of x squared over negative x plus 1. Alright, let's just jump straight to this approach. That's the limit as x goes to infinity of 1 over x squared times x squared. Also, if you're wondering, why am I using x squared instead of x? We always just choose the highest power of x for this technique, whatever that might be. 1 over x squared times x squared over 1 over x squared times negative x plus 1. And that is the limit as x goes to infinity of 1 over negative 1 over x plus 1 over x squared. Okay, so what's going on here, right? If I tried plugging in infinity, I'd get 0 plus 0. And I'd have a constant on top. So we have a constant over 0. We can't divide by 0. That's bad. How can we quantify this? Well, really, this doesn't exist. But we can fudge a little bit and say that this is equal to negative infinity. Okay? Why negative infinity? Well, this term is going to drop away faster than this one, so let's ignore that for a second. That'll just end up going towards negative infinity via fraction multiplication. You know what? I'll do that now with a few more steps, so it's more clear. As x gets bigger, negative 1 over x plus 1 over x squared is always negative and gets smaller. Right? Bigger and bigger x gets, the closer and closer this expression gets to 0, and it's always going to be negative, since 1 over x is always bigger than 1 over x squared, for x greater than or equal to 1. So, we fudge and say that the limit as x goes to infinity of 1 over negative 1 over x plus 1 over x squared is equal to negative infinity. If you were to graph this function, what would it look like? Well, it would have an asymptote at 1, let's see here, if you plug in like 1.5, it would be negative, yeah, shooting down towards infinity, it's always negative. Alright, let me graph this for a second and come back to you guys. Alright, after not wasting your guys' time watching me struggle with graphing a basic function, this is what the graph would look like. So we see that the function is going to be shooting down towards negative infinity as x gets bigger and bigger and bigger. So we fudge and say negative infinity. The limit as x went to negative infinity of our function would be positive infinity for the exact same reason. So yeah, rule of the day, don't trust an indeterminate form. Always try to do something with it and make it make sense. Alright, I think that's all for now. See you guys in the next video.